Good afternoon, everybody. My name is Brian Gorenc. Look, quick introductions. My name is Brian Gorenc. I'm the manager of vulnerability research. We're going to be talking today about abusing Adobe Reader's JavaScript APIs, and we hope you enjoy the presentation. So today, a kind of quick agenda of what we're going to be talking about. First, we'll introduce ourselves and our research project that we did. We'll talk about the attack surface that exists in Adobe Reader's JavaScript APIs, kind of areas that most people have not thought about yet. And we'll talk about how you actually look for vulnerabilities in this JavaScript API set, what to look for, how to find them, and then finally we'll close with constructing the exploit and chaining the vulnerabilities together to actually gain remote code execution. So, a quick introduction. Again, my name is Brian Gorenc. I work at HP Security Research Organization, and I'm the manager of vulnerability research. My primary responsibility is running the Zero-Day Initiative, which is the world's largest vendor-agnostic bug bounty program. The program has been in existence for 10 years, celebrating our 10-year anniversary. And over these last 10 years, we've purchased over $10 million worth of vulnerabilities and exploit information from the community. We've disclosed over 2,000 public advisories to help fix a large percentage of Internet Explorer's use after free vulnerabilities, Java's sandbox escapes, and now Adobe Reader's JavaScript vulnerabilities. I'm also responsible for organizing the ever-popular Pwn2Own hacking competition, where we ask researchers from around the world to come to our contest and try to exploit the world's hardest attack surfaces, including browsers, browser plugins, and mobile devices. And we've actually held the mobile version of the contest, mobile Pwn2Own here in Tokyo over the last 2 years. I'll have my partner here introduce himself.
My name is Abdul. I'm a security researcher working for ZDI, which is part of HP Security Research for now. I do a lot of root cause analysis, bug hunting, and exploit development. I work off the Montreal, my own office in Canada.
All right.
Right.
And so besides running the Zero-Day Initiative program and running the Pwn2Own contest, we do a lot of internal research. And so we are bug hunters in our own rights. And what we're going to be talking about today is a set of internal research that we did, which we started in December 2014. And what you can see on the screen here are the patched, or basically all of the vulnerabilities that we've discovered to date, and which ones are patched and which ones are unpatched. They're all at the vendor waiting to be fixed. And in fact, last Patch Tuesday, Adobe released another patch for Adobe Reader, and 45 of those vulnerabilities were on this list in the unpatched section. They're now fixed, and that attack surface has gone away from attackers. Over the lifetime of this research, it's almost 100 zero-day vulnerabilities that we've discovered in Adobe Reader's JavaScript APIs, and we're continuing to do research in this space. So we're going to be talking about the attack surface and the vulnerabilities that exist within them. But before we get started, we need to kind of understand the prior research that has occurred in this area. First, we'll cover a set of research done by a researcher with the last name Molnar. And he was really the first researcher to highlight the JavaScript API bypass issue. He did a presentation, discovered a bug and got it fixed in 2014. And it was fixed. And according to Adobe, this vulnerability could lead to information disclosure. And when Molnar did his presentation, he kind of highlighted how it worked and provided a proof of concept which would disclose information from the attacked computer. And you can see on the GitHub link there, if you wanted to get an idea of that type of research, The next presentation we'll talk about is MWR Labs, where they did an assessment of why would a person bother auditing popular software, with the assumption being that all of the low-hanging fruit and all of the harder vulnerabilities have been discovered, and really, why would you spend your time there and focus elsewhere as a new researcher? And they've highlighted the various attack surfaces that existed in the product, and one of the areas that they talked about was the JavaScript APIs. So again, this research started in December 2014, and the primary reason we did this research is because in the Zero-Day Initiative program, we were not receiving a lot of vulnerabilities from the community in Adobe Reader. And we were very interested in this attack surface because we knew that it was being used in the wild to break into corporations, and we wanted to kind of get an idea of what was going on. And we also wanted to kill as many of those bugs as possible and harden the attack surface so that the corporation would not get compromised from these type of vulnerabilities. This internal research really discovered various types of bugs, and we took different approaches on looking for them. First, we developed a set of fuzzers, which we ran on the JavaScript APIs. We also did code analysis, static code analysis, and looking for vulnerabilities by hand. We also reverse engineered how the shared memory works within the software, looking for vulnerabilities, and we discovered basically every different type of vulnerability that could exist in a piece of software, including memory corruption vulnerabilities, the information disclosure vulnerabilities, use after freeze, elevation of privileges, and the most interesting for us was this JavaScript API restriction bypass. It's really something that hadn't been talked about outside of Molnar's research, and we wanted to explore that area more, and we're going to cover all of that. So what exactly are the JavaScript APIs? Well, they expose functionality to document authors that allow you to generate really complex and interesting documents for the end user. They allow you to interact with multimedia. They allow you to process complex forms. You can do collaboration with the APIs. There's really a large amount of functionality that exists in these APIs available to document authors. And there is security restrictions in the JavaScript APIs, and we'll talk about those in a second, with the idea of privileged context and non-privileged context. You can get a really good understanding of what is available in the APIs by reading the documentation that's available from Adobe, and it kind of documents everything that it can do, everything that you can do. So let's take a look at some of the mitigations that do exist in the Adobe Reader's JavaScript APIs. First, there's this idea of privileged versus non-privileged context. And this is defined in the documentation. And APIs that are available and that have security restrictions on them need to be executed in a privileged context. And you can see in privileged context can only be executed in several spots. When you're executing in console mode, when you're executing in batch mode, and when the application is initializing. And finally, you can execute privileged APIs if you are trusting the document certificate. There is a lot of functionality that is non-privileged, but an example of a privileged API is launch URL, which you see on the slide, which allows the document author to basically pop up a browser at any address that they wish. And you have to be in privileged mode to actually get access to the API itself. If you try to execute the API from what we call the doc context or within a document, you're going to get a security warning like this. Now, as a security researcher or as a hacker, you're not going to want to see this security warning pop up on your victim's machine. It's going to clue them in that there is an attack underway, that you're trying to do something in the document that is security restricted. So the goal is to make sure that this security warning doesn't pop up. There's also the idea of trusted functions, which allow you to execute privileged methods from non-privileged context. And you can see here on the code, this is an example of a trusted function. And to define a trusted function, you do this with the code construct app.trustedFunction. And you can see here AN verifier comments is a trusted function because it has that line in it. And then within that function, the code that needs to be executed in a privileged context is surrounded by app.beginPriv and app.mpriv. And so in this case, app.alert is being executed in a privileged context on line 2027. So why would you use the trusted functions? Well, if you're trying to automate some functionality in a PDF and you want to do a lot of batch processing, you can use these trusted functions to do that and get access to the privileged APIs that you need for your processing. There's also this idea of folder level scripts, which you see on the screen here. And they're inside of a folder. You can put these folder level scripts inside of a folder. It's, as you can see on the screen. And they're used to implement functions for automation purposes. You can use the trusted functions inside of these folder level scripts. And luckily enough for us, Adobe Reader provides the end user a set of folder level scripts upon default installation. They're called jsbytecodewin.bin. And in this bin file, there is a set of JavaScript APIs that get loaded up on an application initialization, and they contain trusted functions which have privileged functionality. All of this will become very important for us when we start doing our vulnerability hunting. All of these APIs are loaded into the root context upon application start. They are exposed to the document author through the doc context, exposed to the doc when the document is open. So we want to get access to the code that is in the jsbytecodewin.bin so we can start auditing that code for vulnerabilities. And you can decompile this code. This bin file is actually SpiderMonkey XDR bytecode. And in this bin, like I said, there's trusted functions and privileged code being executed. Now, Molnar, when he did his research back in 2014, he published a decompiler for this bin file. And the code is available on his GitHub link, and you can actually decompile it, and it will spit out a set of JavaScript that you can then audit by hand. The output of this decompilation is really messy, so you need to pass it through a beautifying process so that you can actually audit the code. And what you see on the screen is, about 10 lines of the 27,000 lines that exist in this JavaScript bin file. And you can see here, you can clearly read that this is the color convert function, and there's some sort of processing going on there that you can then audit for security vulnerabilities. So now we have a really good understanding of the code that exists and what we're going to try to find vulnerabilities in. And so we need to look at how we're going to discover the vulnerabilities in this code base. The first thing that we need to think about is, when does JavaScript make implicit method calls that the application developer may not understand is happening? In this case, there are three areas in which the code on the screen actually makes implicit calls. The first is in the if conditional. It's if argument dot attribute not equal to value. In this case, the attribute property is actually calling a getter function implicitly. And you can actually redefine the functionality of this getter using JavaScript, which we'll explain. The next place in this code where an implicit method is being called is in the app.alert, error, this is not a valid value, plus argument. The plus argument is actually implicitly calling a toString function, which can be redefined by the attacker to change the way the code executes. Finally, there is the setter method on the argument.attribute equals different value. This is actually calling an implicit setter method or mutator method, and you can redefine the way that functionality works in JavaScript to change the value that's coming in, leave the value alone. You can do whatever you want using the redefined setter method. And so how do you actually change the way the code functions? Well, in JavaScript, you can actually overload the method or property using underscore underscore define getter underscore underscore. This will allow you to assign a function to that property, which will do the functionality that you want to do, that say the attacker wants to implement. You can also use underscore underscore define setter underscore underscore, which will change the mutator of a property and will allow you to change the functionality and how that implementation works. The next way to do it is through inheritance using underscore underscore proto underscore underscore. In this case, you can define a new property using an object and assign old object to proto, which will inherit the methods that and allow you to redefine the way that a property works on an object. So I'm going to turn it over to Abdul now, who is going to explain how to audit the code to look for vulnerabilities.
All right. So basically, let's say we decompiled the bin file and we have the source code. So the next step is to choose or to find spots where we should audit, right? So the first thing that we should look for is eval calls inside that specific JS that we decompiled. The reason for this is that if we were able to hijack or gain access to one of these evals, then we're going to secure execution inside the root context, which is the first step to achieve the bypass. So as you guys can see, if we grab through the JS, we have a couple of spots that we can target to hijack the eval calls. So the next step we should look for is a privilege block. Just like Brian explained that a privilege block, basically it's code that lies inside begin priv and end priv. Basically, this block has to be inside a trusted function. So when we get a system eval, we're going to have to escalate, and the escalation should be happening inside a trusted function that contains a privilege block. All right, so the code, this is one of the codes that we can actually hijack, the evals that we can hijack. As you guys can see, AF parse date, it takes an argument called long entry, and this function is exposed to us, to the user. So basically, we can forge long entry, and if you see at the end of this function, there's an eval call that calls the log entry car at. So basically, we can control log entry and forge car at, and gain access to that eval. And this basically gives us a system level or root context eval. And finally, if we were able to do that, we will have to find a trusted function with a privilege block with something inside it that we can hijack. This is one of the functions inside the decompiled JavaScript code. Basically, it's a trusted function with a privilege block. It has 3 arguments. One of the arguments is interesting, which is the C source URL. Basically, the C source URL is passed to the isDocCenter URL, collab.isDocCenter URL, which is inside the trusted block, the privilege block. So the plan here is just to hijack or overload this function with a function that is basically privileged. So in that case, we're gonna be able to execute a privilege function from inside the privilege block. All right. So basically, if we want to chain all this together, we have to find an eval that basically allows us to gain execution inside the root context. And the second step is basically find a trusted function and hijack a method that lies inside this privilege block. And finally, we have to trigger the call. So putting this all together, this is how it looks. Basically, we called AF parse date, and AF parse date will actually give us access to the eval. The eval basically will execute the exploit function. The exploit function contains the code that does the privilege escalation, and basically what I did here is define a new object called collab, and I overloaded the is.center URL method, and I replaced it with app.launch URL. App.launch URL is basically a privilege function, and then I set the proto of collab to app, which is basically inheriting all the methods, all the properties and methods of app and putting it inside collab. And finally, I executed CB shared review security dialog with that specific object that I created. And that would actually secure me an execution inside a privilege block, which lies inside the trusted function. And basically, that's how we can escalate. So I'm going to show you guys a video that demonstrates if anyone wants to execute a privilege API from inside the normal doc privileges, how it looks like. Basically, it throws a warning because you're trying to execute a privilege API, which is app.launch URL in this case, from inside the doc privileges. So just denies you from doing it, pops a warning. So I'm going to show a video that demonstrates the escalation and like a successful escalation. Basically, it triggers app.launch URL, which spawns IE with whatever target URL we want. All right, so before Adobe patched this bug, basically it allowed us to override system objects like collab, app, spell, search. All these system objects, we were able to override them with whatever objects we want, and we can overload whatever method they contain with any methods we want. So this is before the patch. So after the patch, they released a version called Adobe Reader DC, and basically what they did is they denied us or just like stopped allowing overriding system objects. So they kind of secured these objects from being overridden. And from having the methods of these objects being overloaded. So a quick recap, in order to have a successful bypass, we need an eval that's executed inside the root context, and then we need to overload a function that's being called from inside a privilege block, which lies inside a trusted function. Right, so the exploitation part. So basically, when Molnar back then reported this bug, Adobe flagged this bug as an information leakage bug, and that was quite interesting for us. It was a challenge. We wanted to take this to the next step, which is gaining RCE, like code execution, out of this. Basically, if we want to do that, we have to play by the rules, which is basically using the JavaScript APIs that are exposed by Reader. So in fact, what we needed to find an API that would allow us to write data on disk, dump a file on disk. And we need that API to lack some restrictions, basically file types, file contents, and stuff like that. So what I did is I went through the whole API and searched for all the API documentation, and searched for all the APIs that allow me to dump files on disk. And basically, I tried all of them, and I just failed, because basically these APIs are kind of designed in a way that wouldn't allow you to dump files in certain directories of certain types. So they're really hardened. So we kind of gave up on the idea of gaining RC out of this, and just went back to fuzzing and memory corruption, basically. So one day I was designing a module, writing a module to fuzz the collab object. So I went back to the documentation just to read what collab methods and attributes collab has. So basically, Adobe documented 3 methods in collab, which are these methods. So I was kind of curious and went back to Adobe Reader inside the console and wanted to dump all the methods, or just to make sure that Adobe has everything documented. So basically, this is what I got. I found out that that collab basically has 128 methods. So if we do the math, it's basically 125 undocumented methods. And among these methods, there's a bunch of functions that start with URI that are quite interesting. As you guys can see here, there's URI create folder, delete folder, put data, enumerate files, delete file. So as you guys can imagine what these APIs do. So I wasn't convinced that these APIs were not really documented. So I went and I searched one of these APIs on Google, and I found only 2 hits, no information about it. One of the hits is just a risk report from the Australian government that just like a threat modeling Adobe Reader, kind of. So I'm going to go through these APIs really quick, just to explain the arguments they take. So the first one is URI put data. Basically, it takes 2 arguments. The first argument is the path of the file that you want to dump data to. And the second argument is OData, which is basically the data that you want to dump to the file inside the file. So delete folder basically takes 1 argument, which is the path, and that path is the folder that you want to delete, right? URI create folder, just as the name implies, it creates a folder, takes 1 argument, and the argument is the path of the folder that you want to create. Enumerate files is an API that takes also 1 argument, which is the path, and basically what this function does is just lists the contents of the file, of the folder that you want. So it's just kind of directly traversal API. URI delete file, as the name implies, it just deletes a file. It takes the path of the file that you guys want to delete. All right, so now we have like a set of APIs that basically allows us to do whatever we want on disk, right? So just an overview, these APIs are used as part of the collaboration feature that Reader exposes, which is basically allows you to share files, submit them for reviews and stuff like that. So one thing common among these APIs, which is the delete folder, create folder, put data, and this is it. Basically, these are privileged APIs. The enumerate files is basically like you can execute it without being in a privileged context. So you can actually list whatever files inside the directory from the doc context. So one thing in common between all these APIs is that they take a path. Basically, this path is a UNC path, so it has to start with SMB / or file //. So things that this APIs fail at is that they don't really sanitize the path. So basically, you can provide SMB / localhost / C and whatever path you want, and that works quite well. These APIs, they don't check the file type that you're actually dumping to or anything like that. Specifically, URI put data. And URI put data specifically, it doesn't check for the data that's inside the OData object. So if you guys want to dump like an exe file or a DLL file, it doesn't mind. You can just dump it, whatever data you want, whatever extension you want. So what we have so far, so basically, we know that we can dump files on disk using the URI put data method. The file contents should be of an OData object type. But if we think about the OData object, what's an OData object? So basically, we went back to the documentation and start looking for clues about how to create an OData object. And basically, we found nothing. But during our testings, we found out that if we pass an OStream object instead of the OData object, basically it's going to pass. So OStream objects are being treated as OData objects, and it works. So in my screenshot here, I tested the URI put data, basically, the method, and I gave it a path, and I gave it an OStream object, which is created by the stream from string, and I gave it a string. So basically, it just wrote whatever I gave it in the file that I pointed to, which is in this case is a.text. So now we know that we can actually create OStream objects using attachments. So basically, if you attach files to PDFs, you can extract the contents from these attachments and store them in a stream object. So this is a good thing. We can use URI put data to dump the file that we want on disk. But how can we actually get RC out of this? So basically, there are two methods to do that. So the first method, which we call it like the Chowkey method, which is basically dumping a file on the startup of the profile. So basically, you would need the target to log off and log in to get your code executed, or reboot the box or anything like that. And the second method is basically dumping a DLL and waiting for Acrobat to actually load that DLL. And we were able to achieve that one. So just to recap on the vulnerable versions of Adobe, basically all the Adobe versions are vulnerable to this specific attack. The only difference is the reader has sandbox limitations, so it doesn't allow you to actually dump files on this disk because of like all the JavaScript calls are being routed to the broker, passed through the broker, and the broker basically denies that. Acrobat Pro, basically, it's vulnerable because it doesn't have sandbox technology. They're vulnerable on both Windows and Mac OS X. So I didn't include the version numbers because the first time Adobe patched it, we broke the patch. The second time they patched it, we broke the patch. And the third time, which was the last time, we broke the patch as well. And it's being fixed right now, but it's a different vector than the one that I've just discussed. So let's put this all together. Basically, we have to attach our payload, which is a DLL, to the PDF, and then create a JavaScript that will execute when the document is open. This JavaScript should be composed of code that actually extracts the contents of the attachment, store it in an OStream object, and then use one of our bypasses to execute URI put data and dump the file on disk. And basically just wait until Acrobat loads our DLL, and then we're going to have a code execution out of it. So I'm going to play a video that demonstrates the whole chain, which is basically RCE on Acrobat Pro. So basically, the DLL is being open, the file is being dumped on disk, and then we're going to have to wait a little bit to have our DLL loaded. Basically, I got calc. So we use the bypass to gain code execution on Reader, which is under Mac OS X as well. So this is a video that demonstrates two bugs, which is the bypass, and another bug, which is a command execution bug, and it works well. This was on the latest version of Mac OS X, Reader on Mac OS X. So this is the latest version of Reader back then. And basically, we got calc. All right. So in order to actually gain RC out of this, we needed to leverage a couple of stuff, which is a system level eval with a bypass system with a trusted function, hijacking a method call inside a privilege block, and then chaining it with one of the undocumented APIs just to dump a file on disk and gain RC out of it. So this is it. Brian, you want to close this?
Sure. So we'd like to thank you for having us out here. We hope you enjoyed the presentation. We do run the Zero Day Initiative program. It is a bug bounty program. We work with the, researchers and vendors around the world to purchase vulnerabilities and work with the vendors to get them fixed in a responsible way. We really want to thank everybody at Code Blue for having us out here, and I hope you enjoyed the presentation. Is there any questions? this on.
ご質問ある方、挙手をお願いいたします。質疑応答の時間とさせていただきたいと思います。質問いかがでしょうか。で、3列目の方お願いいたします。
I can hear it.
興味深いプレゼンテーションどうもありがとうございます。今回こういう攻撃の手法が提案されているわけですけども、これは検知する方法ということに関して、簡単なのか難しいのかとか、そういうことが分かっていれば教えてください。
Sure. So the question was whether the attack was detectable, basically. So yes, so a lot of the research that we do inside of the Zero Day Initiative program is actually the core output of this research is filters inside of the tipping point intrusion prevention system. And so all of the vulnerabilities that you saw earlier in the presentation, all 100 of them, are being filtered and detected using the tipping point intrusion prevention system and in a zero-day fashion. So we're able to stop the incoming attack because we've done a set of research on this attack surface in helping protect the enterprise prior to the vendor releasing the patch.
それはちょっとシグネチャーベースっぽい話なのか、ちょっと中身を解析して、JavaScript として解析してるとかってそういう、手法なのか、そういうどっちなんでしょうか。
Yes. So in our case, for the tipping point IPS, it is a signature-based detection.
ありがとうございました。
Thank you.
それではこのセッション終了とさせていただきたいと思います。ありがとうございました。Thank you, Abdul.
Thank you.
Brian.